As we said in the previous video where we introduced the magnetic field, or the B field, we said that B fields arise from two places. One is in a permanent magnet. That's a rather complicated view that we're going to largely avoid in this sequence. And the next source of magnetic fields are from moving charges, charges that move. So you can immediately contrast that with what you know about electric fields. And if we have a positive charge like this, there'll be electric field lines going in all directions like that, pointing away from the positive charge, and of course into negative charges. And so we know that a charge that is not moving, it's just stationary, is a source of an electric field. Well, in this case here, so stationary charges are a source of electric fields. Moving charges are sources of magnetic fields. And that's what we're going to discuss in this video here. The law that's going to guide us is called the Biot and Savart Law, the law of Biot and Savart. And it's written down as follows here. There's a bunch of constants out front, u naught over 4 pi. And then sort of the difficult part to deal with in the equation is this part here, which is the qv sine theta over r squared term. So if you look very carefully at it, we can clearly see the fact that the charge has to be moving, because there's the q, the charge right there. So if you have an object that with no charge on it, this will be 0 and b will be 0. And also it has to be moving, so it has to have a v, it has to have a velocity there. And obviously you can see if v is 0, b will be 0 also. So this aspect right here, these two terms right in here, or sort of that proof or that link to a moving charge. Charge has to be moving. So the next aspect of the law is that, well, there's something about a sine theta and an r squared. So let's just get the definitions of those out of what they mean here. So the first thing is that theta here is the angle between v. Remember, velocity or the speed is a vector. The object has to be moving in a certain direction. So although it's not written as a vector up there, I'm going to write it here. So it's going to be the angle between v and the line to the observation point. Angle between v and a line to the observation point. Very confusing, I'd say, but we'll talk about it here. And of course, r here, which leads to r squared, is the distance from q, or the distance from the charge to the observation point. Okay, so two references to the observation point here. One, we have theta, which is the angle between the direction the charge is moving in and the observation point, and r squared here, which is the distance from q to the observation point. So the observation point is all in here, so it's important. Let's get the problem set up and use the law here. Okay, so try to remember those definitions, and we'll just go at it. So here we go. Here's a charge here, let's say a positive charge like this, and it's moving this way. So here's the v. So see, we have a much better setup now for what the speed means, because of course the speed can be moving left, right, up, and down. We'll look at a couple of examples here, but there's the moving charge, has a charge q in it like that. And in those definitions of theta and r, the observation point came up twice. It's important, so let's just set it in there. Let's say an observation point is right here. This right here is my observation point. Now, why so much focus on the observation point? Well, remember we said that moving charges cause magnetic fields. But we have to sort of wonder at some point in space around the moving charge, is there going to be a B field at this point or not? Or if I put a compass at this point, will the needle move? Or if I put a paperclip at this point, will it get deflected, because of the way metal objects get moved around by magnetic fields? So I'm just choosing an observation point right here. That's important in there. So what I can do is, as soon as I have an observation point established then, is I can draw a line from the charge to the observation point. Something like that. And guess what? There's another video where we talk about the r hat vector. This is going to be r, my r hat vector. Now, it's not in the equation explicitly, but we'll get there in just a second here. So we can even label it r hat, or if you want to think about it, that's my r vector right here. And knowing that that's the line that connects my moving charge at this instant, sure, a second later the charge will be down here, but at this instant the charge is here. This connects my charge with my observation point. This is going to be theta right in here. We even do it in a different color. Remember, theta, we said, is the angle between the direction the particle is moving in and the line with the observation point. There's the theta right there. So see, I'm in pretty good shape now. I know what theta is. I know what r is. So now I can plug something in for sine theta and r squared in there. So we don't have any numbers for you, but if you're working some sort of textbook problem or maybe something on an exam, theta might be 30, 45, 60 degrees or something like that. And there would have to be some geometry, some reference point in the problem so you could calculate, say, where everything is. Like perhaps the charge here is going to be right at the origin, the XY, the origin of an XY coordinate system. And that way, this point here, this observation point, will be at some XY coordinate that you can sort of know or figure out or something like that. And from this information, you can get R for R squared and even theta in there to get the system to work out right. So there's all kinds of combinations that are possible when you're talking about a system like this. Where would the magnetic field be? So the charged particle could be here and say moving down that way, and your observation point might be up here. But you shouldn't panic or get too out of control because, well, you know Q, and the particle, you know it has some speed v. Here's the v coming down like that. So really what you need to know is the angle between the observation point and the velocity vector and that distance between the charge and the observation point. So here's our observation point right here. So we can sort of draw the R between the charge and the observation point right there. This is R or R hat. Either way you want to think about it. So you clearly have the distance in there. Now what about that theta? Well, remember, theta is always the angle between the R hat and the R hat and the velocity vector. So this big angle in here would be your theta in terms of plugging into that sine theta right there. And so if you can put all this together, there will be a B at this point, and the law of Biot and Savart allows you to compute or figure out what that B field would be. And so you can just do about any example you can think of in the plane like that. You can switch the sign of the charge, whatever you want to do, but that's the definition of what the theta and the R would mean in the Biot and Savart law. Now there's a couple of kind of interesting cases here, where suppose you have a charge here. We'll just go back to the simple case where the charge is moving in this direction with a speed v like that, and suppose that the observation point is right above the charge like this. I don't remember if we just worked this problem or not earlier, maybe not. So here's the R hat. That's the line that connects the charge and the observation point, and there's the B. Excuse me, there's the V right there, and you're curious about the B field right here. We look very carefully at a case like this here, is you can see that the angle then between the velocity vector and the observation point there is 90 degrees. This angle in here is a big right angle here, a 90-degree angle in here. So what that does in your equation up here is remember that the sine 90 is equal to 1. So that's just going to make this sine term just sort of drop out. And what you'll get then is you get a case here where B is mu naught over 4 pi. And it's just going to be QV over R squared because sine 90 is 1. The reason for pointing this out, I'm sure you know how to do that simplification mathematically yourself. This actually corresponds to a maximum value of B. In other words, with that sine being maximized at 1 right there, the rest of just the numbers that you plug in here, this is the maximum value of B you can possibly get given some amount of charge and some speed at the current distance you're at. Now certainly you could move closer to the charge or increase the speed or increase the charge. All of those things would increase B, but everything else being the same, sine being 1 maximizes that magnetic field. So when the observation point is perpendicular to velocity, you sort of get a maximum magnetic field. And there's another case to look at. Looks like this. Here's a charge here moving this way with some speed v, and there's no one said that. Suppose I want to know what the B field is right here. So the charge is coming at me. I'd sort of like to know what its magnetic field is sort of in advance of its arrival or something like that. Well, all right. You just sort of look at the system as normal here. Here's the V. I need to make that line that connects the charge and the observation point. That's going to be my R hat or my R sitting in there. And I can sort of continue with the problem I want, or I can think about it and go, well, I have this sine theta up here. So what is the angle between the line that connects the charge and the observation point and the velocity vector? Again, what's the angle between V and R hat? In this case here, it looks like to me V and R hat in the same direction, so it looks like in this case here, theta is going to be 0 degrees. So without even doing any more computation on this, I notice that the sine of 0 is 0. That means the B at this point is going to be 0. There is no magnetic field at this advanced point. I'm not going to know the charge is coming based on any sort of magnetic field measurement in there. And the same sort of applies for positions behind the charge as well, way back there. So suppose the charge is still moving that way, and I want to know what the magnetic field is at this point right here. I can get my R in there again, something like this. There's my R vector like that, R hat. And so now if I look at the angle, well, V is pointing to the right, my R hat is pointing this way to the left. What's the angle between V and R hat? 180 degrees. So in this case over here, my theta is 180 degrees. Now what's the sine of 180? 0 again. So the magnetic field over here is going to be 0. So there are just a few special cases, and then also remember the point up here B was maximum, but I'd also get a case down here. B would be maximal down there, in magnitude anyway, because all of these observation points seem to make that 90 degrees relative to 90-degree angle between the velocity vector and the observation point in there. So that's sort of a look at that first source of B fields coming from moving charges using this form of the Biot and Savart law, but we'd like to step it up just a tad bit and formalize the notation just a bit. Another form of the law here then sort of stems from the fact that, well, maybe I'll just write up here again. It's mu naught over 4 pi QV times the sine of theta over r squared. That's the one we just used. But remember now that the sine of theta, we saw that in our cross product video here, where we had something like vector C is A cross B. It's the magnitude of A times the magnitude of B times the sine of the angle between the two angles. This is the definition of the cross product. So it would seem then that does the B field, the Biot and Savart law, involve the cross product because of that sign in there. And remember, we were dealing with two vectors. Even in the earlier cases, we had the vector, the r hat vector pointing from the charge to the observation point, and the v vector. We have two vectors. So indeed it does. And this is sort of the more complete version of the Biot and Savart law that really accounts for that direction. All this stuff is the same here, and Q can't possibly be one of the vectors because charge is just a scalar. It's just the amount of charge on an object. So where's the vector going to come from here? And even the r squared is going to be here in the bottom. That doesn't change either. Well, where the vector is going to come from is we know velocity is a vector, so that's just going to be v vector like that. And you will cross it into, you guessed it, r hat itself. So remember, r hat, we have two videos on it in this series, and it might be a good idea to review them. But again, I look at it in law face value. It doesn't really mean anything in the equation. It doesn't have one particular use. But in this equation here, it means the vector that connects Q and my observation point. Vector that connects Q and the observation point. There's the Q, there's the observation point. That's the role of r hat in this equation. So before I try to process this here, I would definitely need to write all this out and draw it. I would need to be able to recognize where is the charge, where is my observation point, so I get a handle on r hat, and only then can I begin to interpret this cross product here. So that's sort of the more formal form of Biot and Savart law, but you do see the same physical parts of it. I must have a charge, it must have a speed, and then I'll get a B field. But you also be a bit careful here with the cross product, because you know maybe some properties of the cross product here, that if you're ever taking the cross product of, say, A times B, this is going to be 0 if A is parallel to B or A is exactly anti-parallel to B. And by parallel or anti-parallel, I mean an angle between A and B. They're parallel, meaning 0 degrees. That's two vectors that point exactly in the same direction like that. Anti-parallel is a 180-degree case, where one vector might point that way and the other vector might point that way. These two cases also generate a zero magnetic field. So true in Biot and Savart law, a moving charge with a speed v and a q does generate a magnetic field, but of course in certain positions in space, the magnetic field might be 0 because of some geometrical consideration, or just physically there does no magnetic field exist there. Okay? So in a case like this then, we sort of like this case here. Again, a bit more sophisticated here. Let's see if we can hash it out a little bit, interpret the law here. Here's a positive charge moving this way with some speed v. So I have my v vector clearly defined, moving to the right like that. And I can put an observation point, say, right here. There's an observation point. So I'll draw my r hat vector points away from the charge towards the observation point. There's my r hat. Again, r hat, vector that connects q and the observation point. So I'm drawing that arrow in there. There's my r hat. What is the direction of the B field? Well, now it's time to get out your right-hand rule. Check another video on that. We have a video on the cross product which describes that. I'm going to go back and use my wooden model here. So if I look at the wooden model here, it looks like V cross R hat. So V plays the role of my A vector on my model here. R hat plays the role of V here. So there's A, there's R hat. And here's a magnetic field then that points straight up like that. So if I wanted to know the direction of the magnetic field at my observation point, in this case here, it would be a B field. Now I've already got a dot there. I'll just draw it like this. That points straight up at me like that. That's the return of the cross product right here. So my B would be straight up. Let me keep it in green like that. There's my B pointing up. Suppose I move my observation point to here. What do I do now? So I'm off diagonal a little bit. Well, the only thing that changes is V stays in the same direction, but now my R hat vector, which connects the charge and the observation point, points like that. There's my R hat. So I'll use my hand and my wooden model in this case here. The right hand rule I like to use the most, so I point my fingertips in the direction of V, curl it up in the direction of R hat, that's V cross R. My thumb points straight up, so it looks like I'll get a B that points straight up here as well. The wooden model also predicts that, so A is in the direction of V, B is in the direction of R hat, although I can't squeeze these two things because glued together I can sort of get a sense of the general direction. V points that way, R points that way, but no matter how I sort of orient them, I'm seeing the picture in my head. This C still points straight up like that, and indeed it does agree like that. Now the reason that these, if I would sort of make these two popsicle sticks go close together, what that would have the effect of doing is shrinking the length of this third vector, or in other words, B here is a bit weaker than it is right here, but that's the nature of the sine theta in the cross product. As that angle reduces from 90 degrees, as it has from here to here, the resultant B field will be a bit smaller. And of course I can keep extending the analogy. I could find the B field here to be up and weaker, and by the time I get out here, I think we saw in the other case the magnetic field should be zero up there. How do you reconcile all this stuff? Well, it's kind of hard to do with your hand because we just don't have any angle anymore. I don't have anything to curl into anymore. But we have a case here where V is to the right, R hat is to the right, and so the B out here is zero once again. So these are all the simple cases here. Maybe we should just jazz it up a bit and see what else we can find. I'll just sort of make something up here. Suppose I have a particle coming straight at me like this. So I'll say here's the Q here. It's a plus like this. I don't quite know how to draw this, but I'll draw a velocity vector on it right here that's coming straight out at me like that. There's a V coming straight out at me. Suppose I want to know what the magnetic field direction is right here at this point. What is my magnetic field at this point here? Well, once again, I will connect the charge and the observation point with my R hat vector like that. And so what I have now is I have a V coming at me and R hat vector going away. I need the cross product between them. Biot and Savart Law says cross V into R. Do it two ways. Put my A vector in the direction of V like this. Here it comes straight at me like that. Looks like my R hat vector is over there like that. Well, can't do it like that. So I've got to have my A vector straight at me like that. See, there's the A on there straight at me like that. And I want this second vector in the direction of R hat. So I've got to actually turn it like this. So here's my A vector. See, it still says A on it like that, pointing up in the direction of velocity. My B vector is in the direction of R hat. And this third line over here, this is the direction of the magnetic field. So at this observation point here, according to the cross product, I'm going to get a magnetic field, which is going to be up like that. That's the answer. Does it work with my right hand rule? Let's see. Fingertips in the direction of V, that's straight up out of the page like that. I want to curl my fingertips now so they reach the R hat vector. So I'm straight up. I'm going to curl down into the page where my R hat vector is like that. Yep, my thumb points straight up in the direction of V. So that's the sort of the interpretation of the Biot and Savart Law. And furthermore, you can go on with it a bit because it's such a formal notation now. Like, for instance, you can have a velocity vector that might be, 5 I hat plus 3 j hat, just some really weird vector. A bit of an x component, a bit of a y component, maybe in meters per second. And you can have an R hat here that might be way over at, well, let's say the observation point then is something like, say you're making an observation point, your xy point that you want to observe this here, maybe something at 7 minus 4. Okay, that's your observation point. You can construct the R hat vector, and you can look at another video we have late on R hat on how to do that. But in this case here, the R hat vector is going to be the distance from the charge. Now let's specify the problem a bit more here. Let's say that Q is at 0, 0. So you have a charge at the origin. It has this speed right here, and you want to know what the magnetic field is at this xy point. So you sort of have a situation like this. Here's the charge at the origin, 7 minus 4. Let's see, x over 7 down minus 4. Here's my observation point way down there. I want to know what the magnetic field is, given that it's moving at 5,3, and I'll try to visualize the 5,3 a little bit. Let's see, that's 5 units of velocity along x, 3 along y, so the velocity is sort of going to be something like that. So sort of a weird case here, hard to visualize. But in either case, I have a v vector, and I have an r hat vector in there as well. They're all set and ready to go. Bit hard to compute though, but if I just rely on the properties of the cross product here, my r hat vector can be found by just finding the r vector here, which is going to be the square root then of 7 squared plus minus 4 squared. That's how far away from the charge I am. Then of course you want to normalize that. Yeah, I'm sort of doing this wrong. The r hat vector looks something like this. It's going to be 7 units along x hat minus 4 units along y hat. So it's going to be very similar to the xy point. Those are the x and y components along of r hat. But remember, r hat is always a vector of unit length, so you have to normalize then by dividing by the length of the thing, which is 7 squared plus minus 4 squared. That's where I meant to write that there. So in this case here, you can construct your r hat vector. I'll leave it up to you to do all the math, but in either case here, you will have some r hat vector, which has so much in the x hat and so much in the y hat. And you can check another video on the r hat vector where we actually work through the numerics. But in either case, you have r hat now. And with your r hat, which you have, and the v vector, which you have now you are free to compute v cross r using, I think it's called a method of minors, or that technique that you learn in calculus. You can actually get v cross r, which will directly give you all the components of the magnetic field. That's caused by the Biot and Savart law.